Good morning, everyone. I was not aware that it was Hobbit Day. I would have dressed accordingly. Actually, I hiked the Appalachian Trail, which is a trail that goes from Georgia to Maine in the United States 12 years ago. And my trail name, which is a lot like hackers have handles, well, hikers have trail names. My trail name was Bilbo, which was actually kind of appropriate because I'm short, I eat a lot, and when you're hiking, you eat even more. Also, the Appalachian Trail ends at Mount Katahdin, which is this, big mountain in the middle of a really flat area. And I believe the Native American name actually means Lonely Mountain. So I took a long journey and I traveled to the Lonely Mountain and actually carried a little ring with me too. And my name was Bilbo. But anyway, there's lots of similarities between hiking long distances and hacking. One that always stands out to me, it pops in my mind, is O days and 0 days are very different for hikers. Those are days you do 0 trail miles, so they're really fun too. You just sit in town and drink all day. But that's not what I'm here to talk to you about today. Today I'm talking to you about hardware implants for fun and root shells. This is right in line with a lot of what Sergey was mentioning. Basically, we have this world where we trust our hardware, we trust our abstraction layers, and it has probably gone a little bit too far because the capabilities of hardware, particularly the capabilities of someone with a couple bucks to spare in hardware, is pretty compelling when you look at what you can do with some of these hardware implants. There we go. Who am I? My name is Joe Fitzpatrick. My background is electrical engineering with quite a bit of computer science and InfoSec twisted in there. I've been playing with hardware for actually more like 15 years now, 5 years of which was hardware training. I just taught a class the past couple days, Applied Physical Attacks on x86 systems, another class similar that focuses on embedded systems. Before that, I was doing hardware and pre- and post-silicon pen testing of desktop and server CPUs for a tiny chip company, as well as internal training for functional validators to include security in their assessment of importance of certain bugs. Can we adjust the screen a little because stuff's falling off? I wonder if I can do that. Let me think about it. So as a little bit of background, I like to incorporate other thoughts and ideas into my talks. Tao is like the Chinese philosophy of the absolute principle of the underlying the universe. And so I was thinking, like, what's the Tao of hardware, right? Hardware is the absolute that underlies the entire world of computing. Everything we do, every code we run, every interpreted scripting language that we write in, eventually whittles down to hardware underneath it. Today, on the other hand, is kind of this concept in Chinese philosophy of inner power and integrity. So that the Te of these implants that I'm building is that if we can understand and harness the inner strength of minor addition to hardware systems, we can have pretty incredible power over everything that runs on it, every bit of code, every bit of software, every bit of scripting language. And the author of Tao Te Ching, Tao Te Ching, is that the, yeah, Lao Tse, said, do the difficult things while they are simple and do the great things while they are small. So let's make little tiny hardware implants to get us our root shells instead of having to chain 15 software vulnerabilities and sandbox escapes, because that's just hard work, and it's software, and software is difficult. So before 2013, we had hardware implants, but what our minds and what we thought of hardware implants was very different. This is a tiny little USB keystroke logger. You plug it in to your keyboard, your system, you plug your keyboard into this, or much better, someone else's would be the idea, and you can log every keystroke that they send. You take this off later, you bring it to your system at home, you plug it in, and you press some magic key sequence, and it spits out every keystroke that they've typed over the past week, month, year, however long you've had it in place. The other thing we had are these game console modifications. Everybody likes to back up their video games because what would happen if you had a flood or a fire or someone stole all your computer, your cartridges, actually they're not cartridges anymore, your CDs or DVDs or discs for your game console. So you want to make backups of all these, and you want to play these backups. So you go and buy these little chips that cost maybe $10, $20, $30, and they're very user-friendly. If you've never soldered before, these are still made for you. You line this chip up in just the right spot. They tell you exactly where to solder, 5 or 6 touches of solder, and suddenly you have installed a hardware implant in your system. And this hardware implant lets you bypass the restrictions that prevent you from playing your legally purchased backup copies of your computer games, as well as your homebrew code as well. So all of this changed. This is what we thought about with hardware implants. This changed about 2013 in December. There was this catalog that was leaked that advertised a so-called NSA toolbox of spy toys. It had all sorts of very interesting things that the media thought was kind of magical. Several of us disagreed, so we got together and implemented our own versions and called it the NSA Playset. You can check out nsaplayset.org to find all the toys that we've developed. All open source, open hardware, so you can go and implement them yourself. The point is, what was magic, according to the media, nation-state capabilities was actually pretty basic hardware engineering and open source and hopefully doable by any teenager in their garage or even younger who can solder some wires together. So what? Malicious hardware implants are real. Hardware implants don't live in a vacuum. What was a key takeaway for me is I was looking at this leaked catalog. All of these hardware implants were designed to give use hardware access to give software privilege. Once the software had privilege, you didn't need the hardware anymore. You could let some software person figure it out. And as we all know, there's tons of software conferences. There's tons of software developers. This is a hardware conference. So if we can shuffle off all that work to the software people, all the better. We can focus on the fun stuff much longer. So today I've got 5 hardware implants that I've developed. Some of them are similar ones that are repurposed in different situations. So what I'm going to do is I'm going to blindly escalate privilege in a system using JTAG. I'm going to patch kernels via DMA on an embedded device. I'll enable wireless control of an off-the-shelf PLC. I'll hot plug a malicious PLC expansion. And I'll go a little into bad USB style display adapters. So, some of you have heard some rhetoric about how junk hacking is kind of killing the InfoSec and killing security. People go to a conference and they present, yeah, I bought this piece of junk from a store and I opened it up and I hacked it. And the argument is, well, there's not much to be learned. We know that junk is not secure. The problem is junk hacking and critical infrastructure hacking are the exact same skill set, and the critical infrastructure stuff is very poorly designed as well from a hardware security perspective. So when you go to a conference and you see someone talk about how they opened up a webcam or opened up a router or opened up any embedded system, all those techniques apply to PLCs and medical devices and cars, just like they apply to network routers and webcams and everything else. So first, if we want to blindly escalate privilege using JTAG, how many people here have used JTAG before? Probably a lot more than most conferences. So I don't have to go into details about the layers of JTAG and how you have pins that control a state machine. The state machine gives you control over device-specific operations, and then we can do boundary scan, we can halt resume, we can do memory access. I gave a presentation last year, JTAG to root 5 ways, because I noticed hardware people think, oh, once you get JTAG, you win, right? Software people think, oh, once you get a root shell, you win. So let's connect the dots. Here's 5 ways to go from JTAG to root shells. So this one particular one goes through memory and modifies a user process. Getty is a process that runs and sits there and waits for you to try and log in. When you go and enter a username, it passes that username onto the login executable, which goes and asks you for your password and processes that. These 2 dashes in here, in this string inside the binary file, those are dashes that are part of a string that's expanded and turned into a shell command. The dashes also mean that no command line parameters should be parsed beyond this. If we change that dash dash to dash f, we actually are telling Getty to instead force authentication, meaning when I give you a username, so I am Getty, I'm running as root, I give you a username, and I'm telling you to force log in as this user. Don't ask them for the password, just log in as that person. So what we can do is we can bypass the need to enter a password. This is one NSA Playset toy I developed. It's called SOLDERPEEK, which is a play on the name Flux Babbitt, which was the name that was mentioned in the NSA catalog. And SOLDERPEEK is basically an Arduino board that plays back a script of JTAG commands that's stored on a little EEPROM right there. Very simple PCB, 2 major components and some supporting passive components. You can use OpenOCD to prototype this. You sit there with OpenOCD, you go through memory, you find the thing, you modify it, you modify that byte in memory, and you get root shell. So what you can do is you can log everything that OpenOCD does in that time and turn that into an SVF file, serial vector format. Store that file on the little EEPROM, and then we have a video of doing that. So here's a Galileo. It's an x86-based development board. It's plugged in and powered up to my system, and I'm trying to log in, right? Of course, I log in as root, and it asks me a password. I don't know the password. Just to make sure you know it's a good system, I'm going to log in as a user. Galileo, password A. Yay, we can log in normally. So we want to get around that. Let's exit. Now, our board is connected over a serial cable. That's how we're talking to it. We're going to get a SOLDERPEEK that's been pre-programmed. Luckily, this is a development board, so it has a JTAG header easy for us to access. That device is already prepared with the SVF file. I try to do it with one hand because I'm holding the camera with the other hand. I now have a tripod, which makes this a lot easier. And it induces less motion sickness to you guys. And this is hardware skills, like real hardware hacking skills, plugging cables in with one hand while there's a plastic thing in the way. So once it plugs in, it's getting power from the device. It powers up the board, no lights or anything, because we want this to be hidden. Basically, it's going through, it's running that JTAG script, it's going through and patching several locations in memory. And if we go back over here, we go and log in as root, and bam, we're in. We just bypassed that. And just to be sure, you know, we can cat etsy shadow, see the shadow file, and yes, we have in fact logged in as root. And it's just any account too, so if we exit, we can go log in as a user as well. Oh, yeah, do it again, whatever. The point being, now we log in as a user. There we go, just user Galileo. Likewise, it's not going to ask us for a password. Log in as anything we want. Just that time we're a plain old user, which is boring. Anyway, so onward. So, oh, I don't have a so what slide. Well, let's move on. Patching kernels with DMA on an, oh, that's out of order. Oh, so what? Implant hardware is simple, cheap, and readily available, right? That was Arduino Pro Micro with one other chip, less than $5 of like built completed hardware. When the headers exist, installation is really quick. I prototyped that payload with standard open source tools. The pin amount is adaptable. You can make a custom header on that board for whatever target you have. It's nice and small and easy enough to stick in lots of places. And JTAG is JTAG is JTAG, mostly. I've tested this same exact thing on ARM, on MIPS, on x86. Obviously, you have to change a little bit of the content of what you're doing, but the overall process stays the same, and the hardware implant stays the same as well. So, second, patching kernels via DMA on an embedded device. What is DMA? This is kind of a map of what a PCI Express system looks like according to the PCI Express SIG, according to the standard. At the very top, we have a CPU, and then we have a root complex, which is kind of the top of the PCI Express hierarchy. What you'll notice, though, is the memory lives under the root complex. So the path from any endpoint on PCI Express to memory doesn't necessarily involve a CPU. There's also a path from any PCI Express endpoint to any other PCI Express endpoint without the CPU being involved. All these software people think like the CPU is like the brain of the operation, right? But really, like, you know, like it's the root complex that's in charge of what happens on this system. There is some history to DMA attacks. About 10 years ago, Joe Grand built this board, Tribble. It was a PCI device which had a PowerPC processor on it that would periodically go and dump the contents of memory to a hard drive. There's also a FireWire card, add-in card shown here. There's a whole class of FireWire vulnerabilities where you plug a FireWire cable between two systems, and just by nature of the system and features that are supported by default in FireWire, you can do DMA access to another computer externally. I was looking for something a little more generic. I found this chip and reference board, a PLX USB 3380, and I've been using it for poking at PCI Express DMA text and all sorts of systems. Typically, you think of PCI Express as something that exists in your desktop computer, and you plug in a graphics card in your computer, and you can play games, or crack hashes. But you can also do this on embedded systems too. So this is a NVIDIA board, and it's got a mini PCIe slot. Intentionally, the intention of that slot is for what's it called? Wireless adapters. But PCI Express is PCI Express is PCI Express. Plug it in, use some electrical tape to hold it in place, and I can do memory access. What impressed me is right off the bat, this device actually had memory protection enabled. So rather than put effort into that, I moved to a different platform. This is another embedded system that I have. This is a Pogo plug, a network attached storage device. It's just an ARM CPU, 800 megahertz, but I know from looking at the spec that there's PCI Express on a couple wires. So just very carefully solder some wires in there. You need to put some capacitors on certain lines. Wire that, oh, I don't have another picture. Wire that around, solder that to a socket, and plug a PCI Express card in. And now we have the ability to do DMA access on this $10 home consumer electronics device. This is the one I'll show you a demo of. This is a wireless router, and it's got a CPU, a MIPS processor. It's got some extra radios, so you can have 10 billion different channels, hog the entire bandwidth to use all for yourself, because who cares about your neighbors and their ability to use Wi-Fi? This one's neat because it's got a SATA, PCI Express connected SATA controller, and there's a spot to plug in a hard drive. It's also got an extra PCI Express slot in case you wanted to put, what's it called, a 4G module or something else that was on PCI Express. Of course, PCI Express is PCI Express is PCI Express, so I just plugged my device in there and held it in with electrical tape again. And looking at this block diagram for this CPU from the datasheet, right there, it's got PCI Express, three different connections, so I can plug stuff in there and do what I want, and of course connect to the DRAM controller and go and do stuff without worrying about the CPU. I wrote some attack side software, basically some Python, that would let me read and write memory. And again, I'm going to go and target a part of the kernel where we do file system access list enforcement. Basically, we have this generic permission function. Is the user permitted to touch this file? It returns yes or no. No would be in the form of negative E access. If I can go and change the spot in memory where negative E access is returned and put that as 0, right, then it returns true and we win. So here's a video. Totem to MediaTek. So here is, actually we don't need video audio on this one, it's the later ones we do. So this is the wireless router. It's a MIPS-based router. It's got some antennas. It's got chips on it. It's got some flash that stores the firmware for it. It's got a SATA controller that's connected via PCI Express, and it's got my device that I've plugged in there. That USB cable connects to my laptop, to my implant. That serial cable connects to the console. And I'm logged in right now as a non-user. If I were to go ahead and try and cat Etsy Shadow, or look at the permissions on it, it's root only. So if I try to cat it, I can't do it. Over here, I've got a script that's going to go and patch generic permission. So it's detecting my implant device, talking to it over USB, patching generic permission at the address it knows it can find it. And that's the device. That device just sent DMA commands over PCI Express, and sorry about the motion. I should be able to cat Etsy Shadow, and basically any file access permission at this point in time will pass. So there we go. Yay, we win. We got the file. If we want to clean that up, we can go unpatch it. Basically patch the original value back into memory. Takes a moment to identify the device, do the memory transaction, restores the value, and it's done. And I should be able to try and cat Etsy Shadow, and it should not work. Come on. There we go. Cat Etsy Shadow, permission denied. So just change a byte in memory, and this is what you, actually it's a D word in memory, and you can control access to the system. So in this example, it wasn't really a standalone implant because I had my USB cable attached to the end to a PC. But this device does have an 8051 CPU in it, a little microcontroller, so I could theoretically port my 20 to 30 lines of code, compile them for this CPU, put it right in the firmware on this device, and it would be a standalone device that maybe I could put a button on it to trigger it, or I could just have it timed to wait till a certain time of day, or wait till an hour after the system is booted and apply the patch. So the next implant I'll show you is enabling wireless control of an off-the-shelf PLC. This is where we're moving away from the toys and junk and into the critical infrastructure, which maybe some people would disagree on the level of detail in the design. So this is a Siemens S7-200 PLC. It's pretty old. I borrowed this from a friend. This is what got me started on PLCs. I'm like, oh, PLCs, those sound like fun. Let me find one. And this is what I could get. So of course I open it up. That's what I do. We found a CPU, we found memory, and we found flash. Something inside me was expecting this to be like all custom hardware, custom silicon, but in all reality, this is much lower volume than consumer electronics, so you're going to find much more in terms of off-the-shelf components in lower volume devices. Pull that off. I have another layer of circuit board. This layer has output buffers and input buffers. All the chips are marked. I can find data sheets for everything. I figured that out basically because we have output pins up here and input pins down here, though. The bottom layer has some capacitors and basically your transformer to transform all your voltages. This is the board that's interesting to me. Like, anybody can play with software, but I like the hardware side of things. So I look around and I figure out that this header connects to a bunch of these chips that are one side. These headers connect to those chips, which is another set of the buffers. If we look carefully, this connector over here is kind of a tiered connector that hooks up to the next layer of the board and connects to I/O pins, GPIO pins of the CPU. So all we need to do is get control over one of those pins, intercept it, snip it, solder a wire on both ends, and we can use our little implant. This is a $2 Arduino board, a $1 Nordic semiconductor radio, and there's probably like $1 worth of wire in between there too. So again, under $5. Build this little implant, put it in a plastic bag so it doesn't short anything out, and so I can put the top back on, and the case is open right now, and you can't see the implant. Right? That's pretty cool. I mean, someone could open it up and say, has someone tampered with this? Open it up, look, oh, looks fine to me. It's good, let's go. Pop the case back on, it looks just like it did before. So I went to go and do like a demo of this one, and I'm like, oh, okay, I just gotta program a simple bunch of stuff in here. Except it turned out to be really difficult to get the software to program this thing. The point, though, is I made this change with no software changes. All the original hardware is there, and the modification isn't apparent from the outside. Since I couldn't find the software to configure and control the S7-200, legally find the software, I decided to just get a different target system, so I got a newer S7-1200 and did the same thing. Open it up. We have a board with a CPU. Oh, I'm missing a... There's a picture of a board. The upper board has a CPU and memory like before. This bottom board has a header, which connects to the input and output buffers. And then there's a power board underneath. I was focused on this board. Here's where I knew that these output lines came from. I traced them up to the upper board, and I know up here we have little LEDs that show us which outputs are on and off. I check out the LEDs. I see they're connected to these pins. These pins are down here. I follow traces to this chip, which buffers them and puts them to that header up there. And on the other end of the header, I follow it, and I have a bunch of resistors here. This is 4 resistors in one package. And 1, 2, 3, 4 are the 4 outputs. What's really convenient about this resistor is it means that I can do whatever the heck I want over here, and it's not going to cause problems on the other side. I'm not going to short out the CPU. So all I had to do is solder that one wire on there and get some power and ground and plug this implant in there. So let's see if we've got the video. This one needs sound. So it beeps really loud, so maybe I'll lower it for you a little bit. So we've got that implant. I've soldered a ground connection near that capacitor, a power connection, which I knew was power because I could find the specs for that chip, and the one spot that I found that would control the output. I'll put it in there, get those wires tucked in nice and neat. And I'll, again, one-handed, I'll reassemble the PLC. Woo. And then pop the lid back on. What's really neat about these is the lids snap right on and they snap right off, and there's no scratches or any marks on them. So, you know, there's no indication that it's been modified. We have our inputs and power. Output is connected to a multimeter in impedance, in conductivity mode, so it'll beep and tell us the resistance when it's shorted out. I'll go ahead and turn it on. And it's telling me up the top that one switch is switched and none of the outputs are on. I have it set up with a simple set-reset circuit, so it's set, the multimeter is beeping because the output's cleared. I reset it, it goes off. So I'm going to go over now, and I have another similar implant. It's basically the same radio and the same device hooked up over serial to my laptop. I could as well put this in a little dongle remote, and I just override the output. 1 to override it to 1, 0 to override to 0, and Z to disable. So you can see when I do it, as soon as I do a 1, the light doesn't go on, but the multimeter is telling us the device is on. Right? $5 of hardware. You can put this in a little car remote dongle type thing. And we can also override the output. Right now it thinks the output is on, but it's clearly not. Another possibility is, you could go in and mess with it and write software to do it really fast, because sometimes that makes things break, and go and flip it on and off the relay really fast to see what happens. I hear noise happening. If you do it a couple million times, you might break out the relay and win or lose or blow something up. So what's the point? This is a very, very cheap implant. A couple, like less than $5. It's almost completely off-the-shelf open source code. I basically took an Arduino sketch, cut and pasted it, and changed 2 or 3 lines. And that's the extent of what's involved in making this. This can be retrofitted to most I/O types if you know where to solder the right wire to. Again, this is basic electronics, and we're applying it to undermine assumptions that have been made about the security of devices. How long is it going to take someone to go in and pop that off and solder something on and put it back together if it's in an unsecured location? How difficult would it be to go and infiltrate a supply chain and put something like this in a system? I don't have answers for that, but I think it's pretty easy. So let's move on. We have another PLC we can talk about, and this is going to be a hot-plugged malicious PLC expansion. So this is the cheapest PLC I can buy in the United States, and I figured I'd buy one. It's a Phoenix Contact Nanoline something. And of course I open it up, easy to open up. The first thing that jumps out to me, because I'm a hardware guy and I play with a lot of electronics, is anything jump out to anyone here? No? 10 pins in the right formation, right there. Like, as soon as I see that, I'm like, oh, ARM processor, JTAG port. And sure enough, it's an ARM processor with a datasheet readily available and a 10-pin JTAG adapter. I can look at the datasheet for this. I know that the JTAG pins are right here. I ohm it out and double check. Yes, it is JTAG. Of course, this chip has code security features. Code read protection lets you lock out people from using JTAG. You can do different modes where you enable or disable JTAG completely, or just run control, or just flash. Different microcontrollers have different features like this. Luckily, no one ever uses them. So, at least on this system, it wasn't enabled. I have a view from the front, and if you look, this is the opening that you can plug in these expansion modules, right? Right now, there's 2 blanks in there, but this is how you would program it over USB. You plug this guy in, it hooks up to that 8-pin black header, and gives you a control over that. But right next to it is this header, which is really interesting to me. So I get, let's take a step back. The way that the GPIOs on this chip are modified is through a memory mapped address. So basically, if we can read and write to a certain memory address, we can find the right GPIO pin that corresponds to our output and write the right values in the right registers. And you just got to dig through the documents to find the right one. If we look at the device, we have these relays. These relays are what take the GPIOs and turn them into on-off switches. Oh, I thought I had one more slide where I describe what I'm doing. Oh, yeah, no, the video will show you the pogo pins that I use. So, last video. Sound still on? Totem for Phoenix contact. So, same setup as before. I've got a PLC with some wires attached that are hooked up to a multimeter that beeps when the switch is on. This one has a controller input where you can go and directly turn on or off any outputs, and I turn it on, it goes on. I turn it off, it goes off. But then I have my implant, and those little pins right there are pogo pins, and they're going to line up with the right pins of the JTAG header that I need to send some JTAG commands. Pogo pins are pretty neat. They're little like sheathed springs, so really good connectivity when you have to plug something in or take something out. You use them for test rigs. I pop it in. The device gets power. It's the same implant as the first one. And 5 seconds later, it goes and writes 0 to the GPIO pin and turns on the device. I can go and use the controller to turn it back off, because when I turn it off, it's going to go and overwrite the GPIO output. But pop it out, plug it back in, 5 seconds, and we start beeping again. So, you could program it to be 5 seconds. You could have it hook up with a wireless radio so you have remote control over this like the other one. But basically, we're using JTAG on an embedded device to modify the outputs of the GPIO without the software really being aware. So, JTAG could be disabled. It's usually not. Test headers are quick and easy to access, especially when you line them up right next to a user replaceable part that can be swapped in while the system is live. This is cool because it can be used on a unit in operation, whereas the other one, you actually had to solder and you had to actually open it up, and you probably don't want to do that while it's on, though you probably could. And when you get JTAG working, you win. That's kind of my philosophy. Like we said before, when you have an embedded system, and you want to talk to software people, you have to speak root shell and translate for them. But on an embedded system like this, when you get JTAG, you win. So the last implant I have to show you, is still a little bit of a work in progress, but I'll show you what I've done so far. I don't know if you've noticed as I'm plugging in my display adapter that the board falls off, because why would you have hardware that you don't take apart? So there's been some presentations and talk about like evil projection and evil video display adapters. This is Blinker-Cough, which was part of the NSA Playset. If you see there's a little thing sticking out of this VGA cable, this component is inside the cable. What it is you would get a bunch of these cables and use them as VGA, and they create an IR mesh network. So if you thought you had a Faraday cage that was keeping your data inside the cage, but it was just a wire mesh, your infrared light would actually be communicating to all the VGA cables outside the cage, and you can communicate over I2C to this device to exfiltrate data. This is Alloy Viper. It looks like a VGA adapter, so a mini display port to VGA adapter that you might go and walk up and say, oh, I forgot my adapter, but luckily you have one for me. Turns out it's actually a Thunderbolt cable connected to this device, Slot Screamer, which is that PCI Express implant, and daisy chained to a real display adapter. So you plug it in, your stuff shows up on the screen, you start presenting with your unlocked PC, and meanwhile, someone is under the curtain and behind the podium, like copying your memory. So there's, display technology changes. We want to have something new and fancy, and this is right off Apple's website. USB-C has the capability to connect everything you need, or the capability to connect anything you plug into your computer to anything it wants. So we've got charging, displays, storage, devices. Let's see. Let's look what comes inside. So this is the Apple adapter. It costs $80. It probably had $70 worth of shielding that I had to peel off of it before I could get to it. And I get inside, and there's this giant PCB with a whole bunch of stuff. Luckily, there was a cheap $20 one that was a lot less shielding and just a simple adapter. These are the two Apple ones. This one is the HDMI, this one is the VGA. You'll notice both of them have a very interesting connector that we just saw moments ago. Think about this. You want to hook up a display. Therefore, you need to plug in a device that has a microcontroller that has a JTAG port on it. This is the world we live in. There's no passive display devices anymore. This is the one that I normally use when I have VGA, And you can see right there, that big chip, that does the real work. That turns DisplayPort data into VGA data. USB-C has the ability to transfer raw DisplayPort data, so we're not sending USB packets containing display information, we're just spitting out display. So this is the most passive USB you can get, USB-C display you can get. But we've also got this chip over here, that's our USB power delivery chip. That's the one that says to the system, I am a low voltage device, I want 5 volts at 500 milliamps, so please send me that voltage so I can do my job. Yeah, if it said I want 20 volts at 4 amps, it would get that too, if your system supported it. The next chip we've got over here is a simple like NXP USB microcontroller. This is what you might find in a small device. You could probably wire this to be a USB to serial adapter or something like that, or USB HID device. But the point is, this is a USB programmable microcontroller. And if you ever used DFU util, there's usually some way to program this microcontroller. It just so happens that this one was configured as I bought it. I opened it up looking for like a pin or something that I would pull to put it in programming mode. Turns out you plug it right in and it's already in programming mode. Okay, so I plug this in, I hook up my VGA adapter, I run DFU util, and I can dump the firmware off that microcontroller. And then I can go and update that firmware with whatever I want. So I haven't done it yet. But my plan is I'm going to turn this into like the malicious presentation adapter. So you plug this in, your slides go up on the screen, and then randomly every couple of minutes it advances or reverses the slide for you, because you might as well have fun while you're doing this stuff. When we have one port and that port can do anything, when we have one port, that means that port has to be able to do anything. When that port can do anything, that means anything we plug into it has pretty strong power over our system. Maybe this is like the one ring for the new MacBook. Hardware isn't just hardware anymore. There are no passive devices. There are no passive cables. There's no reasonable way for a user to look at a device and know what it does, right? There's not much more minimal you could make this adapter and still have the right ports on it and realize that it's more than just an adapter. So we went through a couple implants today. We had blind privilege escalation using JTAG. We patched kernels with DMA. We enabled wireless control of an off-the-shelf PLC, and then hot-plugged a malicious PLC. And then I ranted a bit about USB. These are all the implants stacked up on a $20 bill. SOLDERPEEK, a few dollars. Less than $5. This one, which is the wireless radio and another microcontroller, is another $5. This is the one that was plugged into the USB plug, into the expansion module for the Phoenix Contact one with the pogo pins. The pogo pins are probably the most expensive part. This one on the end is the PCI Express device. That was probably the most expensive. It's about $60, $70, but still. $60, $70 is not much when you consider that people think of this stuff as nation-state capability. So maybe I should start selling these for $10,000, or like $10 million, or euros. But so yeah, they cost between $5 and $75. They can be built by hobbyists. They weigh, all of them combined. Oh no. Individually they weigh less than an ounce. I was going to say all of them combined, but no. They can be customized to all sorts of different targets, and they really barely scratch the surface of what's possible with hardware implants. So hardware is cheap. Standard interfaces really are standard. Automating these small devices is pretty trivial. If you have an interface, if you have a protocol, if you have devices that are meant to speak that protocol, then it's pretty easy to mimic that and create your own device that's going to speak the same protocol. If you can't trust the hardware, you can't trust the software. And if you can control the hardware, you can control the software. So there's a lot of ranting and a lot of complaining. So what are the solutions? We can't protect against hardware attacks. Some people will say we can, but I don't believe we can. If you own the hardware and you have unlimited funds, you can get at what you want. We can, however, increase the cost of attacks, and oftentimes a very minor increase in the cost of implementation. Disable JTAG. Don't put debug ports on your board. These things don't cost that much, and they turn it from a $10, a $5 attack into a $1,000 attack or a $10,000 attack. The other thing is, we really must demand documented security assumptions from hardware vendors, right? If we're buying a device from a hardware vendor and they're telling us this is a PLC. This is a piece of network equipment. This is a display adapter. They should say to you, if you want this to be secure, you must secure it. You must install it in a physically secured area. If you want this to be a secure piece of equipment, you must make sure it is or is not connected to these interfaces. When we get manufacturers and vendors to say what their security expectations are, it actually means they might have actually thought about them, which is the first step to starting down the path of making this a little more difficult and a little less trivial. So going back to the philosophy side of the thing, the whole philosophy of hardware implants, there's this story of the 3 vinegar tasters. And there's lots of different paintings and representations of it, but Confucius is the first vinegar taster on the list, and he tastes this barrel of vinegar, and he says it tastes sour, and the vinegar is polluted wine. And this is representative of a conference goer who missed the open bar. Buddha, on the other hand, is in the middle, and he tastes the vinegar, and he says that it tastes bitter. And vinegar is bitter, so it kind of makes sense. But he says, life is pain and suffering. And clearly, this is the incident responder, right? Of course, Lao Tse is at the end. He tastes the vinegar, and he's smiling, right? Why is he smiling? Because he sees vinegar for its positive uses. Clearly, he was a hardware hacker. He goes and he gets some salt and peroxide and mixes it up with the vinegar and uses that to etch some more PCBs. So that is what I have for you today. Do you have any questions? Mike?
In the JTAG attack, how do you find the right address to change?
So in order to find the address that you want to change in the JTAG attack, you have to have prior knowledge of the system. For the first one, the Galileo, I actually found out that as I booted it several times, the process I was looking to attack only ended up at 4 to 5 different addresses most of the time. So for that one, I just blindly wrote to all 5 addresses and got lucky that I didn't destroy anything else in the process. For the PLX Phoenix Contact PLC, I had the documentation for the chip. I knew what the address of the GPIO was, so I could just have a simple script that would write to that address and be done. So.
And the PCI DMA?
Similar approach. Luckily with the PCI, that device is a bit more capable. The JTAG device is output only. The PCI Express device could read and write. So if I wanted to, I could have it programmed to go and read through memory, find the address, find the code that it wants to change, and modify it.
Okay, thank you.
So JTAG is really kind of dumb. It's just a state machine. And attached to that are these instructions that actually go out and do something. How do you map between the vendor instruction and reading and writing memory?
So the way I did it is I used OpenOCD, which worked on the target system, and I recorded everything that happened and turned that into an SVF file. So I didn't go down to the deepest layers of how everything worked. I just did the top layer of I know how to do it from prototyping tools, and then I just captured the dump and turned this raw dump, which is probably about 100 times larger than it needed to be, but did the job I wanted to do. If I wanted to be more clean and precise, I would have gone to the manufacturer documentation and figured out exactly what steps to go through to interact with the debug registers to do the one write that I actually wanted to do.
So your open source library already handled all that for you?
Yeah, I handled most of it. Yeah. I think there were a couple modifications we made to OpenOCD to make sure all the data was there, and then wrote the script to take the raw output log and turn it into SVF. Thank you.